If you're a weather enthusiast, and since you're listening to AMS on the air, I think there's a very good chance that you are, then do we have some exciting news. A global community of weather enthusiasts is waiting for you. The AMS Weather Band, a new initiative by the American Meteorological Society, is a vibrant online community of radar watchers, double rainbow hunters, teachers, learners, and everyone in between. Gain cutting-edge insights about the weather that interests you the most. Share your love of science from wild weather stories to jaw-dropping photos and videos. Gain exclusive access to weather experts plus lots of fun content and interactive features. Learn all about it and join today at weatherband.org. Welcome to AMS on the Air. I'm Dakota Smith.
I'm Jeff Rosenfeld.
And I am Irene Sands. We're here to podcast all things weather, water, and climate.
The question is really, why do tornadoes form in general? We're getting closer, but we're still a ways away. I get this tornado that's just crazy. It looks beautiful. You've got 7 vortices rotating around. You've got some interesting wobbling around going with the central vortex in there. It's just crazy stuff. Sometimes the tornado sends a downdraft out and produces like a little mini downburst that produces horizontal vorticity that then gets advected upwards and tilted and stretched. It's really quite complex.
Hello, and welcome to AMS on the Air, the official podcast of the American Meteorological Society. Today we have an interview with Dr. Leigh, an associate scientist working at the Cooperative Institute for Meteorological Satellite Studies. His research focuses on severe weather, particularly supercell thunderstorms, tornadoes, and downbursts. In this interview, we discussed how he uses high-performance computing to revolutionize this field of study. This interview was conducted in Boston at the 2020 annual meeting, and I can attest that it was a whole lot of fun, so let's get right to it. So thank you so much for joining us today.
Thanks for having me, Dakota.
Okay, so I don't even know where to start with the work that you do. I guess, how did you get started in this field? What sort of led you to it?
Yeah, sure. I've always been a science geek since day one, as long as I can remember. I was always tinkering around with radios when I was a kid and looking at a telescope, I'd be looking at the stars. Got interested in archaeology, went on a dig in junior high school, things like that. But what got me into meteorology, well, 2 events happened when I was young. Our house got hit by lightning when I was like 5 years old. I was in Ludlow, Massachusetts, of all places, which really had an impact on me. It's one of my first memories because it was, there was a fire, there was paneling flying across the room, glowing red wires, the whole 9 yards. Nobody was injured, but my mom couldn't hear for a couple days because of the concussion that, it was really kind of scary. A couple of years later, in the same part of the country, this was near Feeding Hills, Massachusetts, the Windsor Locks tornado that Fujita named was an F4 that went up the Connecticut River Valley. This was October 3rd, 1979. Just missed our house. We had downburst winds at our house, I later learned, and it was really scary. So weather was on my radar, so to speak, very early. Fast forwarding a bit, when I got into high school, we started programming with computers, and I was very drawn to programming. Learned BASIC in high school. And then in college, I took a class on programming that I really liked a lot. I was one of those students who couldn't wait to get out of class to do the assignment kind of thing. It's very geeky. So I would go and program stay at the computer lab all night and get my Pascal program done. And that was a lot of fun. So fast forwarding a little further, get into my core courses in meteorology at the University of Wisconsin, I learned that, programming and weather go hand in hand. And this was in the late 80s. So I learned, wow, this is what I want to do. I want to play on computers and do weather. So I got my bachelor's degree in 1989 and then worked for John Anderson. He was my advisor for graduate school at the University of Wisconsin. Jerry Straka was my TA. For those of you listening, you probably know who Jerry Straka is, a very brilliant meteorologist who did a lot of work on tornadoes and thunderstorms. So I started my PhD work on microbursts, downbursts, which form out of storms. At NCAR, you get those all the time. You get these very deep, dry boundary layers, and you get some rain falling through it and producing these strong downward winds that can do things like cause lots of wind shear for aircraft, which is a bad thing if you're trying to land a plane or take off. But early on, John Anderson, my advisor, was big into visualization. Okay, he ended up leaving academia, going to work for Industrial Light and Magic, where he worked on a lot of the Star Wars movies, The Perfect Storm, things like that. You can see his work in the actual visual graphics and CG stuff, as they call it. Later worked on Pixar, and now works for Google. But my point being, I was really instilled with the whole idea of making weather look really cool and telling us something physical, and that's why I spend so much time with graphics and visualization, aside from the fact that it's really hard to understand the data without looking at it and bringing it to life. I like to do visualization in computers. So I'm one of these tornado scientists. I'm a bit of an oddball in that I'm very interested in tornadoes, but I'm really, really interested in using supercomputers and computing technology to understand more about the physical world.
A lot of the visuals and products that you produce are a cutting edge. They're things that people have never seen before until they see what you've done. Do you ever feel like you're waiting for the technology to catch up so that you can actually make what you want to make?
Yeah, that's a very interesting point, and it was the case for a while. The Blue Water supercomputer that was the recently retired, at least for general science, supercomputer at NCSA, University of Illinois, was the game changer for me. Through a collaboration with Robert Wilhelmsen, one of the pioneers of cloud modeling, I gained access to that machine in the early 2010s, and I sort of made it my mission to run George Bryan at NCAR, his CM1 model, on the supercomputer, and also to do, I've always been interested in high resolution and try to resolve things that I know that a lot of our models aren't doing, just because, it's hard. It really is hard. You can't just take a code and throw it on a supercomputer and it runs efficiently and creates lots of wonderful stuff. So I gained access to the Blue Waters machine, and at that point, once I had some really good results, I realized that this is it. This is really, and I now have the technology I need, but I did need to do a lot of work to manage data and manage the amount of data that the model produced. At this day and age right now, I would say that I'm feeling pretty good. I've got simulation data. I've got tons of data. I just need time to analyze it and other people to analyze it with me. And that's the biggest challenge for me right now. I've gotten to the point where I've succeeded in my goal of simulating certain storms, and we're going to continue to try different environments. But the technology is doing all right. I think that it's just a matter of learning how to harness it right. And, GPUs are now very common, and programming those is a non-trivial exercise for those of us who are used to writing Fortran and C code. Well, C++ now, CUDA, all that stuff. I have a really sharp grad student doing some work with me who's a CUDA C++ programmer who's utilizing GPUs to do trajectory analysis from my history file data. So we're sort of always trying to push the frontier there. And it's not like something we set out to do. It's just that, hey, I have this problem I want to solve, and we need novel techniques to solve these problems because of the amount of data, because of the fidelity, because of the high resolution, because of the fact that I'm saving data as frequently as the model time step, because I can do that now using data compression and other things like that. So, but yeah, it's always good when things run faster. So, I'm looking forward to the day when we have, petabyte thumb drives and computers that are, quantum computers on our keychain. Maybe that's a little crazy, but yes, that's a good question, because there have been times when I've been frustrated with the state of the compute, and I just couldn't get things to go because it took too long, or there's too many hardware failures or something, and it just is very frustrating. Mm-hmm. But due to my circumstances, I've been able to sort of, as a faculty when I was at Central Michigan University, I was able to sort of work on this in the background for many years, and I did my sabbatical out at NCAR, which was great. I gained a lot of knowledge out there for 8 months in the early 2010s, and that was really what got me to sort of get my methods together, and then I've sort of honed them ever since. But yeah, the work that I do is I'm completely reliant on federal supercomputing facilities to do my work. What I do, the kind of work that I do, simply requires the supercomputing technology. And now that I'm on the Frontera supercomputer at TAC, I'm pretty happy with the experience so far. And that machine has a lot of GPUs on it as well, so we're just starting to kick the tires, and we've reproduced some of our early results on Blue Waters. That's great. It's really important that we scientists do that and reproduce our results, especially moving to a different hardware platform, different software platform. So yeah, the sky's the limit, really. It's just having all this data and then trying to figure out how to tease out the science from it. That's the big challenge.
So you've learned a lot, the community's learned a lot about tornado genesis through some of your work. Is there a key question that you're still trying to? Well, obviously there is. You're employed. You're doing the work.
Sure.
But what is that key question that, or maybe a few questions that you want to answer in tornado genesis?
Yeah. So tornado genesis is interesting. It's one of these things it's sort of like the golden key. The brass ring. You're really trying to find. The term trigger comes up, like, what's the trigger that causes the tornado? And I actually don't like that language as much, because what I see in my simulations, so the question is really, why do tornadoes form in general? We're getting closer, but we're still a ways away to be able to discern between whether a storm is going to produce a tornado or not. And let's face it, none of this work is just playing on computers until you realize that the work that I do and hopefully will help our forecasters down the road. This is all about trying to forecast these things before they happen so people can get out of the way if there's enough time. At least from my perspective, that's the important thing. So what I've seen in some of my simulations is that I'm looking at the support structure for the tornado. What is going on in the supercell that enables this tornado to last so long? And that's a different question than what causes a tornado to form, because if you sort of are just focusing on the tornado and maybe some vorticity mergers and stretching and things that we know are important, but I'm looking at a larger, sort of taking a step back and looking at the bigger picture. What is going on inside the supercell that allows the mesocyclone to produce this just tremendously strong updraft that then supports this long-lived tornado? And one of the features we've called this feature we discovered in the model the streamwise vorticity current, which is air that's on the cold side in the forward flank of the storm that gains horizontal vorticity via baroclinic mechanisms from having warm air adjacent to cold air primarily. And then it gets sort of sucked into the updraft and stretched and tilted, and there's a lot of interesting dynamics that goes on. And that seems to play a role in helping to make a very strong low-level mesocyclone. And I'm looking at it from that perspective. So yeah, we can look at no tornado, bang tornado, what happened in that little 5-minute window, and that's important, don't get me wrong, but I'm more interested in sort of, you can sort of think of it as a symphony, and I'm interested in the first and second movement, not just the grand finale. And so I'm looking at what goes on, 15 minutes before the tornado, 10 minutes before the tornado, and what's going on across, maybe a 30 by 30 kilometer box in the storm. What's physically going on? Because those are the types of things that we can maybe key in on radar or something that, if they are important, then they will lead to making better forecasts. And of course, the tornado is important, and the actual formation mechanism of the tornado is important, and there's a lot of people studying that issue, and we will as well. But right now, I'm more interested in, sort of taking a step back from the actual formation of the tornado and just what I would call it like the structural support for the tornado in the storm. How does it get set up in the supercell?
Gotcha. What do you think is the coolest thing you've seen in your visualization so far? I know it's probably a tough thing to pick out, but
no, there's been some wacky. I've done a lot of simulations that nobody's seen, by the way, and this is true for all. It's like one of the dirty secrets of numerical about what their prediction is like. For every simulation you see, there's 10 failed ones that went wrong or something. I've created in my simulations like anticyclonic EF4 tornadoes that initially I thought were just like, there's a bug, I'm just going to run away and screaming. This doesn't happen in nature. Well, there have been actually anticyclonic EF4 tornadoes. They're very, very uncommon. They're rotating the wrong way, essentially.
Yeah.
But they form, sometimes I get these in the sounding I've been using lately. That was crazy. I get these interactions between vortices that are just crazy. And I guess the latest thing that really blew my mind was shown in my talk yesterday, where during the formation of the tornado in my 10-meter simulation, there's two vortices that come together that sort of zip into each other, sort of coil into each other as the tornado forms. And I've just never seen anything like that before. I can't even imagine something like that is detectable in the next, say, 10 years or so, if I try to think of the horizon of where our observational technology goes, because it's, up in the storm where everything's happening, but you get to these crazy vortex-vortex interactions that are just, I could watch this stuff all day, So I have had some interesting results. One of the more frustrating results I had was early on when I first simulated the 30-meter simulation. I got the tornado. I presented my results at the Severe Local Storms Conference in 2014. There was a little issue with the sounding. I had to fix the stratosphere. It was just a dumb thing I did. And I fixed it, and I reran it, and I didn't get that tornado back again. So this speaks very much to the sensitivity to initial conditions that are just rampant in these simulations. And this is a well-known problem. Lorentz addressed this or identified this issue long ago, but there's sensitivities that will freak you out. I mean, I really thought I lost the tornado forever. I'm never going to get it back, and I couldn't have my messed up stratosphere, it would be an albatross around my neck. But as it turns out, the environment's more robust than we initially thought. I got a little bit better. I got the model to run a little bit better. I got my data going better, and I was able to do more simulations. And then, we get a tornado. But every simulation, you can update the compiler or change compiler flags or update the libraries that involve the model, and you will get a different result from the same exact simulation. So these sensitivities, you have least significant bit issues that sort of amplify over time to get different results. Now, how different, you might ask? So I have had cases where the tornado doesn't even form just because I tweak a tiny little knob. It's really crazy. And this is the kind of sensitivity that, does it exist in the atmosphere? When you think of some of these big, nasty events, it makes me wonder if, how different the environment would have had to have been for it not to have formed, if that's a convoluted sentence. But RV sensitivities in the real atmosphere, because you cannot have a parallel Earth that you run a separate experiment on. So yeah, I've seen some crazy sensitivities. I've seen some really weird vortex interactions. But I'm also just, I'm humbled by this amazing, beautiful complexity I see in the simulations. Now, at 10 meters, you start to resolve multiple, the suction vortices in the tornado itself are well resolved, and I get this tornado that it's just crazy. It looks beautiful. You've got 7 vortices rotating around. You've got some interesting wobbling around going with the central vortex in there. It's just crazy stuff.
You mentioned multiple vorticities. I think the first time I really saw that from a real live video perspective was the April 2011 event. There are a few images of, I don't even remember which tornado it was, but there's one point where it's just there's a vorticity.
Horizontal roll.
Yeah, it's rolling.
Tuscaloosa. Yeah,
I think it might have been the
Tuscaloosa storm. There's one video particularly this guy took that's just tremendous. He was very close.
He's in a parking lot.
Yeah, that's the one.
Yeah.
You have a very moist boundary layer, and when you have a boundary layer where the relative humidity is very close to 100%, very close to being saturated, when you have these vortices, they can drop the pressure enough to condense air, and you see you see them with your eyes. And that was an environment where you had a lot of these so-called noodles flying around. You have a lot of horizontal vorticity, and that's seen in my simulations too. We see a lot of that stuff within the tornado environment. There's a lot of turbulence, a lot of crazy flow. Sometimes the tornado sends a downdraft out and produces like a little mini downburst that produces horizontal vorticity that then gets advected upwards and tilted and stretched. It's really quite complex. And I think what we're seeing is reasonable because of storms like Tuscaloosa, where you can see the manifestation of this vorticity in the cloud field with these little noodle-like vortices flying around.
We've had a lot of cool imagery like that, and also this year, I feel like I've seen a few drone videos from above of tornadoes that have sort of changed my perspective.
Yes.
How do those types of videos inform you when you do your work, or does it?
Yes, it totally does. In fact, one of my favorite collaborations is with a guy named Hank Shima. He's known as Pecos Hank on YouTube.
His stuff is amazing.
Isn't it amazing? So he's a wonderful videographer. He gets close to the storms. And I know I've seen some recent drone footage of where they've flown into, there's a small tornado that was, I can't remember where it was, but you can literally see everything. You can see the inflow, you can see the multiple vortices, you can see the structure.
It was over a field, and you could see it in the whatever vegetation there was.
Yes,
there.
And you could and you could also see you'd see cloudiness form, and I was like, is that just stripping rain away from the trees? Is it dropping the pressure, forming condensation? You see the inflow into this sucker. You can see how fast the wind is moving near the surface. You can see the multiple vortices in action. Yeah, that's very informative because I'm going to be looking to make sure the model is doing something similar to that. It's important for us model types to get our heads out of our models and look at the real atmosphere, not forget what's out there. So I am totally on board with these much safer ways of viewing. I don't like people do what they're going to do. They're going to chase storms. They're going to get close, whatever. But I love this drone stuff because you lose a drone, right? It's much different than losing a life. So I'm all for this. I'm always going to be looking for stuff like that because I want to make sure that it's important to me to know that the model is at least doing something that is reasonable so that I don't just live in model la-la land, you know? And I'm very sensitive to that issue because even though I'm not a field meteorologist, that's what's important, what's out in the atmosphere. So yeah, I think we're at a really interesting time right now, both for compute and for observation. And I really look forward to where this is going to go.
Yeah.
Talk to me in a couple of years.
Yeah, I think we're all looking forward to some of the cool new visuals that you produce. So Dr. Leigh, thanks so much for joining us today. We appreciate it.
Thank you.
And that's it for this episode of AMS on the Air. Thanks so much to Dr. Leigh Orr for joining the show. If you want to learn more about this episode, you can find it online at ametsoc.org. To get this podcast in your app feed, click that subscribe button. And, follow us on Facebook, Twitter, and Instagram. We're at AMS on the Air. Thanks for listening and happy weather.